The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The half-life of carbon-14 is 5,730 years. Determine the value of K and the equation of decay for carbon-14. So our first task is to find this value of K in the equation for decay, which is y equals a times e to the negative kt. So here we can plug in a few numbers. The half-life is given to us. That'll be our t value, 5,730. A represents the initial amount of something, in this case carbon-14, the initial amount. Because the half-life is given to us, that means that whatever the initial is, the stuff after 5,730 years should be half of the initial. 0.5a represents the amount of carbon-14 5,730 years later, after it's disintegrated from the initial a value there. E is our log, or natural log base e, and then t, like I said, was 5,730 times k. So that's our first task, is to isolate and solve for k. So here we are. We have 0.5a equals ae to the power of negative 5,730k. The first task would be to eliminate the a values. If I were to divide both sides by a, they would simplify to 1. So that's task number 1, is to get rid of those a's, because now the only unknown variable is k. 0.5 is what I have on the left. E to the negative 5,730k is here. The unknown variable k is in my exponent, therefore I will be taking the logarithm of both sides, but because we see base e from section 7.7, we learned that we will go ahead and take the natural log of both sides. Because of the cool fact that the natural log base e of e is 1, we could swing out the exponent out in the front and make it negative 5,730k times the ln of e, but the ln of e is 1, and so we're left with negative 5,730k, which we will divide both sides by, and that'll give us our k value. So let's pause the video, get your calculators out, and go ahead and plug it in. The natural log, let's see, the natural log of 0.5, and we're going to divide that by negative 5730, and we get 1.2096 times 10 to the negative 4. So here we can write it out like this: 1.209 times 10 to the negative 6, or excuse me, 4, not 6. So if you type in that in, you should get 4 here. That's great in scientific notation, but what we want to do is write the k value in standard form. So let's take this decimal and move it to the left 4 times. So we will, let's see, 1, 2, 3, 4. So we're going to have 1, 2, 3, 3 zeros. K is equal to 0.1230, and then 1209. You can round it off after 3 or 4 decimal places. So there you go. There's k. That is the rate of decay when you plug it in your equation there. Now, the last thing it wanted, and what's k value, and the equation of decay. Putting it all back together now, y equals the substance of carbon-14 at the end is the initial times base e to the negative kt. Well, k is 0.00012, and then times t. So that would be the other thing that we solved for. A paleontologist examining the bones of a prehistoric animal estimates that they contain 2% as much carbon-14 as they would have contained when the animal was alive. How long ago did the animal live? Well, first off, how long ago means that we will be solving for t. You must first find the equation for decay of carbon-14 using the fact that the half-life of carbon-14 is 5,730. We already did that. in the previous slide. So we're going to rewrite this equation, AE to the negative 0.00, whoops, it's supposed to be a negative sign there, negative 0.00012 times t. So it's asking us how long did the animal live if we have a paleontologist saying, hey, there's about 2% as much carbon-14 as it has now as it used to be alive. So what we'll do is instead of y, the stuff at the end, we will replace it now with 0.02 of the initial a when it was 100% of carbon-14 when it was alive. So this is where we're at. We're solving for t, and the thing that I'm trying to solve for is in the exponent. It's up in the exponent, so we're going to have to take the natural log of both sides. But before we do that, we will cross off the a's, and we'll be left with 0.02 equals e to the negative power, or e to the power of negative 0.00012 times t. So as I was saying, because we've isolated our base, we can now take the natural log, 0.02 of both sides. The natural log of e to the negative 0.00012 t. We'll swing this exponent out in front, and so we have ln of 0.02 equals negative 0.00012 times t, because ln of e is now gone, it's equal to 1. So here we are. T equals the quotient of the natural log of 0.02. We plug that into our calculator, divide that one by the negative 0.00012, and we get approximately 32,600 years, 0.19. So we can just round it off to 32,600 years. That's how long ago this animal used to be alive, because of the fact that it contained 2% as much carbon-14 as it would have when it was alive. If prior research points to the animal being around 20,000 years old, then this is a separate problem. So we're going to set that equal to t. All right. How much carbon-14 should be in the animal? How much carbon-14 should be in the animal? So the y, stuff at the end, equals AE to the negative 0.00012 K. And what we're going to do is plug in, K. K is that value. It's T is what I needed to put here. There we go. T. So what we'll do here is we'll take the initial value of when the animal used to be alive was 100%, or 1. Times e to the negative 0.00012 times 20,000. Oh boy. Let me clean this up here, guys. Sorry about that. 20,000. There we are. Okay, and we'll go to our calculator and we'll say base e to the power of that product, and let's see what we get for our answer. The study tip on the left there says, when given a percent or a fraction of decay, use the original amount of 1 for A, and that's what we have been doing here. Okay, here we go. To the calculator, we say that base E is the shift ln. So it already takes your base E to the power of, and then we will put a parenthesis here, negative 0.00012 times 20,000. And that value comes out to be 0.090717. And so a percent, this is a percent written as a decimal, so what we will do is multiply by 100, and we will say that it's approximately, let's write this right here. Whoops, not that. This guy. We will say it's approximately 9.1 years, give or take. Oh, what am I doing here? Not years. Sorry, guys. Not years. Go back to the question. 9.1% of carbon should be in the animal of carbon-14. Okay. The population of Phoenix, Arizona in millions can be modeled by the logistic function below, where t is the number of years after 1980. So we have a function here, f of t equals 2.0666 divided by the quantity 1 plus 1.66 times e to the power of negative 0.048 t. That equation will be given to you. Part A, we in class messed around with some calculators and we graphed this thing, and it looks like this on the right. We adjusted our window and we messed around with the trace function to identify this horizontal asymptote. And as we saw, as numbers from 1980, as numbers increased on this trace function, as we picked more and more values, larger and larger for t, which is the number of years after 1980. For example, if we plugged in 10 for t, that's the year 1990. If we plugged in 100, we're talking about the year 2080. What we found out is that logistically, the population of Phoenix cannot grow indefinitely because we would be overpopulated. We would run out of resources. We would be in serious trouble if the trend continues. So logistically, it has to level out somewhere, and that represents part B, the horizontal asymptote. Well, what we found is the horizontal asymptote is your numerator. 2.06 million people is sort of the maximum capacity, if you will, of Phoenix. The trend will continue, but it won't ever pass that amount due to the fact that, people pass on, people move, etc., etc. So part C here, will the population of Phoenix increase indefinitely? No. If not, what will the max population be? That goes back to part B, in that the horizontal asymptote represents the numerator of the function that will be given to you. Part D, here we go, especially important here. Put a star next to this guy. According to the function, when will the population of Phoenix reach 1.8 million? So we're going to put a star next to that one. And we want to know when it's going to reach 1.8 million, because right now, at time 0, it looks like we're what? At time 0, we're in 1980, and it's about maybe 0.9 or 1 million even. They want to know when it's going to reach 1.8 million. So what we will do is for f of t, we will plug in 1.8, this stuff at the end. 1.8 million, when is it going to reach that amount? Equals 2.0666 divided by 1 plus 1.66 e to the power of negative 0.048 t. Whoops. So we're trying to solve for t here. We're solving for t. That's the goal. Okay, so the first thing I will do is I will multiply both sides by the denominator of the fraction, 1 plus 1.66 e to the negative power negative 0.048 t. And if I did that, I would take 1.8 times that quantity, like so, equals 2.0666. Okay, so the point here is I'm trying to solve for t, so let's isolate my base e. Let's isolate it. So what I will do now is divide both sides by 1.8, divided by 1.8, and that'll give me 1 plus 1.66 e to the negative 0.048 t equals, let's see, 2.0666 divided by 1.8 is 1.148111, repeating. Now, I am going to save the rounding until the very end. So what I will do is I will prevent myself from rewriting that quotient as a fraction that I would eventually round off. I want to save the end to round. So I'm going to go ahead and do everything until the very end when I plug it into my calculator. In this moment, I should subtract 1 from this quotient. So 1.66 e to the negative 0.048t equals this quotient here. And if you know how to store a particular value as a letter in your TI 84 or 83 or 89, by all means go for it. You could replace that quotient with, say, the letter A, so that you wouldn't have to keep it there until the very end, but either way, it'll work out this way as well. So to isolate my base, I would now need to divide everything by 1.66. So e to the negative 0.048. Now finally my base has been isolated. We're going to divide this 2.066 over 1.8 minus 1, that's a quantity. All of that divided by 1.66. What we'll do now is we will take the natural log of both sides so that we can then swing up this negative 0.048t. And so what we need to do is take the natural log of everything up here. Let's see, can I go up or down here? So the natural log of, let's see, how could I write this? 2.066 divided by 1.8, that's a quantity, minus 1 over 1.66. So this right here, guys, will represent one number, the natural log of that quotient, your numerator, the quotient minus 1, divided by 1.66. And I wish we were done, but when you figure out that quotient, what's next is to take this negative 0.048 and divide it by this guy. So with your calculators, follow along with me. T equals, we're trying to figure out how long it's going to take for Phoenix to reach 1.8 million. So here we go. I want you to type this in as I speak it. 2.066 divided by 1.8. Okay, that's 1.14777. We're going to subtract 1 from that. I'm sorry, guys. It's 3 sixes, I believe. That'll mess things up. So let's try it again. 2.0666 divided by 1.8. 1.1481111. Repeating. We're going to take that number, subtract 1 from it, divide it by 1.66, and we get 0.089. Well, I want you to take the ln second ans of that number, and you get negative 2.416610139. Divide that number by now negative 0.048, and we get 50.346 years, in approximately 50 and a third years here. The population of Phoenix will reach 1.8 million.